Antonia is a postgraduate student, a master's student in computational linguistics under Sara, and she received that degree from Uppsala University. And sorry if I'm mispronouncing that. Focusing on argument mining, and is currently looking for exploring the prospect of doctoral positions in artificial intelligence with a focus on like education. And Sara is an assistant professor at Uppsala University in computational linguistics, but studied at, let's see if I can pronounce this, Linköping University with a focus on machine translation. Sorry for my American pronunciation of these things. And she's currently focused on cross-lingual methods for dependency parsing. And as a special interest on the impact of training data.
Yeah. Okay, so as Joe said, my name is Sara Stymne, and I will give this talk jointly with Antonia Karamolegkou. And we'll talk about transfer language choice for cross-lingual dependency parsing. So we divided this talk into 3 parts. I'll start by giving a background on cross-lingual dependency parsing, and especially on language choice, transfer language choice. Then Antonia will take over and talk about the case study focusing on parsing Latin. And then I will have the last part presenting 2 other studies on a more diverse set of languages and also taking domain into account, and then finally wrap up. So to start with, I assume that you probably know what a dependency tree is. So it's on top of this slide. So in a dependency tree, words are connected by arcs that also has a label that describes the type of relation. So in this tree, you can see that this is the subject of is, tree is the root, and it is connected to copula and the determiner and so on. And this can be contrasted to phrase structure tree, where group words into phrases like noun phrases. So when you do dependency parsing, it's quite natural to use the universal dependencies tree banks, which is a large collection of tree banks. So currently there are nearly 200 tree banks in over 100 languages. And the nice thing about UD is that it's there are guidelines that are harmonized across languages. So there's a universal taxonomy where languages can select from a common pool of categories. And it's also possible for languages to have language-specific extensions. So there are, of course, a lot of people involved into creating all these tree banks. So hundreds of contributors at the moment. So just as a bit of a motivating example, so here are 3 tree banks that existed before UD came about. So the English sentence here, a cat chases rats and mice, is translated word by word into Swedish and Danish, but you can see that all these trees are different, even though they actually have the same structure, just due to different conventions being used, different label sets and so on. So the only arc that's the same between any of these tree banks is the green one, the direct object that connects rats and chases. Otherwise, they're different. We can also see this blue arc, the conch, which actually exists in both Danish and English, but it has a different semantic. So in English, it connects the 2 conjuncts, and in Danish, it connects the conjunction with the conjunct mouse. So, and the Swedish one, it has partially the same, the subject has the same structure as English, but the object is different. But the labels are completely different, so there's still no real match. So you can imagine that if you want to do some kind of cross-lingual learning, it's hard to learn when the annotations are this different, and it's also very hard to evaluate. So maybe you manage to parse quite well in the kind of English annotation style for Swedish, but how would you evaluate that when the Swedish one expects a different structure? So that was the kind of motivation for starting UD. And this is the type of annotations in there. So there are morphological features. I shortened them a little bit to fit them on the slide. It's a little bit of information, more information really. There are part of speech tags. There are lemmas and words, and then there are this dependency annotation, which is formatted in a specific way that are guided by guidelines. And in this talk, we will only be concerned with the dependency parsing. We won't care about part of speech tags and morphology and those other things, which are also interesting, of course, but you can't do everything. So just as a further example, so this is an example from the PUD, the parallel UD tree bank. So it's a tree bank with 1,000 sentences that have been translated, and it exists for around 15, 20 languages, something like that. And here you can see that the structures are often parallel between languages. So in this example, the English and Swedish trees are nearly the same. The only difference is that the adverbial is placed before the verb in English and after the verb in Swedish. But except for that, the structures are identical. And the nice thing about having this consistent annotation scheme is that the annotations are now the same. The labels are the same. And you can take another language like German. You can see that, again, the structure is more or less the same as Swedish. The only difference is that the verb in German also needs a reflexive and a particle. But otherwise, so it's quite feasible that if you train a cross-lingual system now, you could probably learn between these three languages. Of course, all sentences aren't as similar as this one. I cherry-picked this one. But even so, there are many similarities between these three languages, which are relatively closely related. But of course, things don't always look this nice. So here's two languages that aren't related to English. So we have Korean and Finnish. And here you can see that just a few arcs are shared. I marked them in blue, the ones that are shared between English and the other two languages. But the order of words are quite different. So you see that this subject arc is now a long distance relations, whereas it was quite short in English. And then there are also some type of structures that we don't see in English, like an adverbial clause, a compound, and so on. And in Finnish, this is a copula constructions, which leads to a completely different sentence. So intuitively, it's probably less useful if you want to have a good English parser to use language from Korean or data from Korean or Finnish than to use data from German and Swedish. But the issue that we're going to be concerned with here in this talk is how do you choose the languages, the transfer languages that you can use in a cross-lingual model. Here's also an overview of the sizes of the different tree banks in UD. It's a few releases back, but the distribution is still the same. So you see that there are very few super large tree banks. There's quite a few reasonably sized. So for these tree banks, you can train a very good parser, monolingual one. But there are also a very high number of languages where you have very small tree banks. Some of these, you just have test data. You might not even have any training data or dev data. So for those, you can't really train a good parser, or if you can train one at all, monolingually. But this is at the same time a really great test bed for cross-lingual methods, because we have these harmonized annotations. And we also have, especially for the smaller tree banks, quite a diverse set of languages from a high number of different language families. While the larger ones are predominantly Indo-European, there are some exceptions like Japanese. The small ones have much more diversity. So this is really nice for this type of work. So then going to cross-lingual parsing, I just thought I exemplify some methods that have been proposed. So one early method was to use the lexicalized parsing. So the idea then is that you don't parse based on the word forms, you parse based on some other representation. So typically people would use part of speech tags. So then you could train a parser in a source language, for instance, English, where you have good tools, but you don't train it based on the word parse, you train it based on part of speech tags. And then you can apply this parser if you have part of speech tags for another language. So one issue here, of course, would be that if you have a language where you don't have a parser, you're also not very likely to have a part of speech tagger. So that's a problem, of course. And also the results weren't all that great, especially when the languages weren't very closely related. Another type of strategy is different types of data transfer. So the idea then is that you transfer the annotations to a target language, and then you can train the parser directly on the target language. And there are different approaches for how to transfer annotation. So one is annotation projection. So the idea then is that you have some parallel data. There's quite a lot of parallel data around. Then you parse the source side of the parallel data for a language where you have a good parser, English or German or something like that. And then you can project this English or whichever language you use annotations to the target language by using word alignments, because the data is parallel. Of course, this is quite noisy because structures are different in different languages. Their word translations aren't one-to-one, so there's quite a few little tricks you have to do to make this work, and the resulting annotated corpus will be quite noisy, but you can still use that to train parser. That performs reasonably well, I guess you could say, even though it's far from perfect. Another option is that you take your tree banks that have been annotated by humans. So the annotations will be better than if you parse as you do in annotation projection, and then you machine translate the tree bank. So the translation then wouldn't be perfect. So there's a trade-off if you want human authored text or machine translated, or if you want human annotations or parsed. But the principle then is the same, that you can transfer the annotations, and the kind of issues that you meet are also the same, with structures being different and so on. Another strand of work is joint models, where you train a model for several languages at a time, and often then this assumes that you have a little bit of target data, but could of course also train models of many transfer languages. And what's been quite useful is to add language embeddings to this, so that you have a representation of which language a sentence comes from, and then the system can kind of learn similarities and differences between languages and take advantage of that. There are also quite a few models based on different types of multilingual representations. Another example was to use cross-lingual word clusters. But of course, with the advances in neural networks, there are also now many methods that are based on that, so that use different type of cross-lingual embeddings or multilingual language models like MBERT. And the idea for these type of models is actually quite similar to the lexicalized parsing, but instead of using post-text as a representation, you use these multilingual embeddings of different types. And of course, they tend to be much more informative representation of languages. So the idea again is that you can train the language and parse it in one language and then just apply it to some other language because the input format is the same. But since these models are much more expressive than part of speech tags, these tend to often in many settings, but not always, as we'll see in later in the talk, but they can often give very good results. And we will focus today on different types of joint models. There are also other ways you can divide different types of cross-lingual methods. So one is what the target of the parsing is. So in one line of work, people have tried to find a parser that gives an overall good performance across a range of languages. So maybe a universal parser, if you wish, that you can use for any language that you like. So a couple of examples of this are UDify and UDaptor, which are trained on a high number of languages. UDify was trained on all the languages in UD at the time, and UDaptor was trained on 13 languages, but which were selected to be quite diverse. And in UDaptor, they also take advantage of typological features. And then these parsers are applied both on the training languages, but also on other languages, typically low resource languages, which don't have any training data. And both of these give quite strong results, but of course, it's much harder to get good results for these low resource languages. Another line of work is to focus on the performance for a specific language. So some studies doing this is the one by Vanjadal, who focuses on 3 different low resource languages, and they pick one source language for each. And Mitchell and Madden did a similar study currently, but they use 3 different source languages instead. And this is the kind of line that our work also will be concerned with. So then we come to how to choose these transfer languages, as I already touched on, which will be a theme for today. And a very common strategy is to select a language that is related to your target language. It belongs to the same language family, or has a small phylogenetic distance in the language family tree. And this is done in many different studies. Some of this I already mentioned. And this can often work very well when you actually have a closely related language which has an available tree bank. But of course, that's not always the case. There are many languages where there might not be a closely related language at all. And even if there is, that language might not have a tree bank. And even if there is a related language, it's not always the case that the related languages share the same linguistic properties. They might have developed differently throughout the history. So of course, there are also other strategies that you can use. So I will just exemplify this by some strategies we have tried to use in our own work coming out of the parsing group in Uppsala. So in our Connell 2017 submission, we tried to use 4 different criteria. So here we trained multi-source models where we used more than one transfer language for translating into very low resource languages. So we used, again, genetic distance as many others. We also picked languages that were geographically close, because contact languages, of course, can often influence each other. Since our parsers are using character embeddings, we try to include a language which shares the same script. And we also looked at the development performance in a zero-shot setting, thinking that the languages that work well in a zero-shot setting might also work well in a joint setting. But of course, this requires us to have a little bit of data for the target language. And in this case, we had roughly 20 sentences per language. So of course, these estimates were a little bit shaky. And in our Connell 2018 submission, we again used genetic distance. And then we also tried to cluster the tree bank of the language embeddings coming out of a model by training a model on relatively little data, but from all available training languages. So the intuition here would be that the languages whose language embeddings are close in this space, they would probably also be useful in a cross-lingual model. But we found also that this was quite noisy. When we compared clusters from different runs, it wasn't very consistent. It was hard to find consistent clusters. And most of the consistent clusters, they were actually from closely related languages. There are a few exceptions, especially different ancient languages that Antonia will get back to. And what we did not do, and what's not done also in the work of many other works in this field, was to explore any of these strategies in depth. We thought they were kind of good criteria, but in some ways they were a little bit ad hoc, because we didn't really explore this, except for some extent with this clustering. So luckily, some people have actually investigated this in a systematic way. So I will spend a little time on a study by Lin et al. Called Choosing Transfer Languages for Cross-Lingual Learning, which I presented at ACL 2019. I think this is a very nice study and one of the few that really looks at this issue in some detail. So they investigated the impact of different factors on transfer language choice. They also created a ranker, which they call LangRank, for ranking transfer languages based on these features. And they apply this to 4 different NLP tasks. So machine translation and part-of-speech tagging, where they have a joint training set up, and entity linking and dependency parsing, where they had a zero-shot set up. And the features they used were 2 different types. They used what they call dataset features, where they actually used the dataset from the transfer and the target language. So things like dataset size and ratio between sizes, type token ratio, and word and subword overlap. And of course, this requires you to actually have some data for the target language, which is not always the case. But then they also use different linguistic distances based on the URL typological database, which has vector identifications of languages drawn from different linguistic databases like WALS, Ethnologue, Glottolog, and Foible. So the distances they used there was geographic distance. So this is, of course, a little bit of an abstraction because it's hard to pin down exactly where a language is spoken in many cases, but it gives some kind of measure about how close areas where the language is spoken are. Genetic distance, which is the distance in the word language family tree. And they also have the cosine distance of different feature vectors. They have phonological distance with vectors from WALS and Ethnologue. Inventory distance, which is also phonological distance with vectors from Foible. Syntactic distance with vectors from WALS. And then I have what they call featural distance, which is a combination of all the other feature vectors. So it covers all these 5 other distances. So here are the main results from that paper. And you can see that in all cases, so they created this ranking, I should say, by using a variety of decision trees. And in all cases, at the bottom here, the LangRank is when they combine these features, either all of them or just the dataset or URL features. And on the top, they use just single features. And in all cases, it's better to use LangRank, either on all or on the dataset features. If we focus on parsing, which we'll focus on today, it was also reasonably good to just use the linguistic features. If we look at individual features, we can see that the best one are word overlap, phonological distance, and geographic distance. Phonological distance I find a little bit curious. They never really explain that, but you would think that syntactic distance would be a better measure for parsing than phonological distance. But yeah, so this is still a little bit of an open question. And here is also an example of a a decision tree. So this is for machine translation into Galician because that's what they had in the paper, but they say that this holds quite a bit, quite often across tasks as well. So you can see that the top deciding feature is actually the genetic distance. So if there is a close enough related languages, it's better to choose that. Only if that's not the case, they fall back to these data set features, like here's the ratio between the size of the transfer and the target language. So, I mean, in many other studies, and what we also find that seems to be the case, that if we actually have closely related languages, that's always good to use. But if we don't, then the choice of transfer language gets a lot harder. These studies that I talked about, they were for the case where we just target a single language. But nowadays, of course, a lot of people use these different types of zero-shot models based on multilingual LLMs like MBERT. And in most cases, English is used as a transfer language. Of course, that's partially due to availability of data. But there is actually a recent study by Turk et al. Which explored this in this setting as well, using MBERT and MT5. It's not for parsing, it's for tasks like XNLI and QA. But and then here they target a diverse set of possibly unknown target languages. And they find that across these 4 tasks that they have, that German and Russian often tend to do better than English. And this is actually the case even when they machine translate the training data from English, which is a little bit curious. Of course, you can't machine translate data for all tasks. It's much harder for parsing than for XNLI, for instance. But it goes to show that this issue is important not only in the setting that we're going to talk about today, but also in a wider set of kind of setups. So finally, I'm going to say a few words for this session, part of the talk about our parser. So the parser we'll use in all our experiments is the UU parser, the Uppsala University parser. It has a bi-LSTM-based feature extractor based on the model by Kipper-Wasser and Goldberg. It's transition-based. There's actually a graph-based version as well, but we're only using the transition-based. It has an arc hybrid and swap transition model. So that means we can also parse into non-projective structures. And it uses a static dynamic oracle. And it also has cross-lingual models, and it uses language or tree bank embeddings. So essentially for each language or for each tree bank, we have an embedding, and then the system learns this embedding during training. So it can represent similarities and differences between different tree banks and take that into account when it learns to parse languages. So I'll just show this quickly graphically as well. So assume we have these input representations for each of the words. The brown fox jumped in this example. Then we have a forward and a backward by LSTM going over the words, and we concatenate these representations for each word to get the context-sensitive representation of the word. And then we take the top words on the buffer, assuming to be this one in this example, the top word on the stack, and feed this to multi-layer perceptron, which then predicts the next action that the parser should take, which could be left arc, right arc, shift, or swap. And in this way, we incrementally build up the dependency tree for each sentence. The word representation in the most basic version of UU parser, it has the word embedding, which is randomly initialized at training time and which is learned as part of training the parser. You could also add an external word embedding, different types of cross-lingual embeddings, or I'll also show some example where you use MBERT embeddings. And we also have character-based representations where we run by LSTM over the characters in the word to get a representation of the word based on characters. And that's quite useful, partially because it can carry morphological features and suffixes and things like that. And then for cross-lingual models, we also add this tree bank embedding. So for each word, it knows which tree banks the sentence where it came from. And if we just use one tree bank per language, this boils down to language embedding. And it's also possible to set it to that. So here's just an example of the type of results we can get with this model. This is our Connell 18 shared task. So here we also used external embeddings and also post tags embeddings, which I didn't have in the image. So for 82 tree banks that we had for this shared task, we used 34 models. And this was mainly by grouping languages of related languages, and in a few cases also other languages, and also grouping languages monolingual in some cases. And then we compare this to using a monolingual model. And here in the table, I just put 4 languages, which I find to be quite representative. And we can see that we tend to get improvements. And the improvements are large for low research languages like Kazakh, but from a very low level. So this is not a great parser because there are only some 20 sentences available for Kazakh. For other languages where we have more resources, we can still see quite nice improvements, and especially for languages like Slovak or Swedish, where there are closely related languages, Czech for Slovak and Norwegian for Swedish, with quite large resources. For other quite large tree banks like Finnish, we hardly get any improvements at all, but it very rarely hurts. Of these 82 tree banks, it was only in 4 cases we got slightly worse results for a tree bank, and then by not in no case by more than half an LAS point. We can also see this here, that the average gain for the low resource languages was over 7 LAS points, but even across all languages, and here there are some very high resource languages as well, we get an average gain. So we tend to get better improvements for low resource languages, but it's also the case that it rarely hurts to use this model, even for high resource language. And then of course this also relies on us quite carefully selecting which languages to use in these groups of languages. Because when we try to use too large group of languages that are more distantly related, results sometimes got a little bit worse. Yeah, so that was the end of our first part.
Great. Would you like to pause for questions, or do you want to move into the next section?
Yeah, I don't know if there are any questions. We're happy to take them now.
I have a couple, but I want to let other people ask.
So I have one question.
Yeah.
So you mentioned you used tree bank embeddings to help inform the system which languages to choose.
Yeah.
So did you also try with language embeddings when you concatenate all the tree banks from one language?
Yeah.
So were there any differences there?
Yeah. Yeah. So in one study we did this monolingually, and then we found that we overall got consistently we got better results by having tree bank embeddings than just concatenating all the tree banks into one. And
okay.
it depends a little bit on the language. When we done this cross-lingually, we haven't really explored it as much, but we don't tend to get worse results when we use tree banks embeddings rather than if we use language embeddings instead. So this tends to work. There is a little bit of an issue when you want to apply these models to some data that isn't in a tree bank, because then you need to set the tree bank embedding somehow for your test data, and then it's not always useful. But in many cases, the tree banks embedding actually boils down to language embeddings if you only use one tree banks per language. But especially monolingually, we have shown that it can definitely help rather than concatenating.
So in regard to the same question, I just wanted to know that, so when you're using the tree bank embedding, so is it that the closer languages, their kind of performance is good rather than the languages which are not closer enough?
Yes, so we'll show some results of that later in the talk. But typically, I mean, as a kind of general rule, it's easier to get improvement if you have closely related languages, but it's not the case that it's always the most closely related languages which is best. But we will show some results about this later in the talk as well.
Okay, thanks.
And when you were reviewing the last slide, you were mentioning that there were very few instances, but some instances still that that the cross-lingual actually cross-lingual methods actually was did cause a decrease in performance, and but it was for specific languages, and I was just wondering if there was any sort of consistent characteristic across those languages where performance fell, that any characteristics that were consistent amongst those languages.
Yeah, so actually for this shared task, we didn't only do dependency parsing. We also did word segmentation, sentence segmentation, and part of speech tagging. And for some of those languages, we actually did really bad at the segmentation. Oh, not really bad, but we didn't do all that. So that might have played the role. So I mean, so we don't actually evaluate only the parsing in isolation here. We also evaluate the other two. But otherwise, we couldn't really see any clear patterns. I mean, for the low resource languages, I think it helped in all cases. So I also think that all these languages had reasonably sized pre-bank. But we don't know exactly why. And it was in none of the cases it hurt all that much. It was relatively small differences.
Got it. Thank you. And then I guess going back to what you were talking about on slide 16 with the with lang ranks performance, it seemed like the performance jumped really significantly. Like it increased for all those tasks, but it increased particularly significantly for, thank you. It increased particularly significantly versus link distance methods on machine translation, which is obviously a notoriously difficult task. And I was just wondering if you had any thoughts as to why, like, that task in particular received such a huge bump.
Yeah, I don't really know. I don't think they really have a good explanation either. I mean, in all these tasks, they also have a different set of languages. So I think sometimes the languages you have can play a role. They discussed this a little bit for the entity linking, that there were quite some languages there that were quite closely related, and there it was quite easy to find a match. But then there were a few languages that didn't really have a good match, and for them it kind of just jumped around and was hard to kind of do anything. Because so I mean, it could be issues like that. Maybe there was just more of a spread, so it was more challenging for that set of languages. But I mean, this is just speculation. I don't really know.
Got it. Thank you. Yeah, no, and I'm asking very specific questions. So
yeah, and I mean, it's not my paper either. I mean, we should have had the authors here, of course.
Got it. Yeah. No, thank you.
Yeah. So I'll just stop sharing then and let Antonia share instead.
Great. So you can all see me and hear me? Yep. Okay, then I start. So in the previous section, we saw a brief introduction in cross-lingual dependency parsing and transfer learning. And now we will focus on the case where we target a specific language, Latin, and especially on how to choose good transfer languages. We explore the impact of similarity features, including genealogical, geographic, and syntactic similarity, and also the impact of different text types and training set sizes. And the goal is to parse Latin in a low resource scenario. And this paper was published in the 23rd Nordic Conference on Computational Linguistics, Nodalidad 2021. And we performed some experiments using Latin as a low resource language, and then 2 languages from the Italic branch of the Indo-European family, Italian and French, and then 2 languages from the Hellenic branch, Ancient Greek and Modern Greek. That's the only languages in the Hellenic branch anyway. But what is the motivation behind this language choice? So the motivation was based mostly on the Uppsala submission to CON 2018 that Sara mentioned before. And they trained some monolingual models compared to multilingual models. And the grouping of the languages was based on clustering tree bank embeddings. But even though most of the clusters were mostly for closely related languages, there was also a tendency for tree banks containing old languages, such as Ancient Greek, Gothic, and Latin, to cluster together. And one reason for these languages parsing well together could be that several of these languages come from the same annotation projects. And as we can see from the table, 4 of them come from the ProEL annotation project, and 2 of them come from the Perseus annotation project, containing consistently annotated data, and in some cases, partially parallel data. Example from the Bible or the New Testament. So the researchers did not investigate further the reasons behind this clustering. And in our study, we wanted to investigate this. And we tried joint training, which is a method that Sara mentioned before in cross-lingual dependency parsing. And we trained models with Latin and Ancient Greek, Latin and Italian, Latin and Modern Greek, and Latin and French. And we tried to investigate 3 factors: how the training size affects the parsing results, how the tree bank content affects the results, and finally, we used the linguistic distances from the real database that Sara mentioned before in the study by Lin et al. And we examined language similarity. The tool we used was the Uppsala University parser, and the evaluation metric was the label attachment score, which is a standard evaluation metric for dependency parsing, and it uses the performance of words that are assigned both the correct syntactic head and the correct dependency label. Now, the Uppsala University parser was mentioned by Sara in the previous section, and in our study, we just used the default settings and hyperparameters. And since there are some tree banks created by the same annotation projects, and we have similar content, such as Perseus and Proel, we tried more than 1 tree banks for each language. And in this way, we wanted to examine whether the content of the tree banks and the fact that they have parallel data in some cases affects the results. And for Latin, we used Perseus, Proel, and ITTP tree banks, all the available tree banks actually. For Italian, we used the ISTD tree bank and the VIT tree bank, and we tried to have tree banks with similar content, such as news, articles from politics, or Wikipedia articles. And then for Ancient Greek, we used the only available tree banks that we have, which is Perseus and Proel. For Modern Greek, the only available tree bank, but thankfully it has a similar content to the other tree banks. And then for French, we preferred the FTB tree bank because of the content. It is about news and politics articles. And we can see from this table that there are tree banks coming from the same annotation projects, and they have some similarity in the genre of the data. Perseus uses almost parallel data from the Bible, both in Ancient Greek and Latin, but it also uses some classical texts, which are completely different. In Latin, we have Latin authors, but in Ancient Greek, we have Ancient Greek authors. So these are not parallel data. And the same applies to Proel, because we have parallel data in the New Testament, but then we have completely different classical texts. And we also use the ITTP tree bank, which has Latin classical texts, but they are not about politics. They are completely different. All the other Ancient Greek tree banks have classical texts from historiography or philosophy, while the Latin classical texts focus more on politics and battles and nothing to do with philosophy, most of them. So these are our experiments. We first trained a monolingual model with 250 and 500 Latin sentences because we want to imitate a low resource scenario. And then our multilingual experiments have 2,500 sentences of transfer languages. And then we also increase our target language from 250 to 500 using 2,500 transfer sentences. And then we increase the transfer sentences from 2,500 to 10,000. And in this third experiment, where we increase the transfer language sentences, we could not include Modern Greek and French due to lack of data. So let's see the results from our first multilingual experiment. We can see, first of all, that comparing the 250 and 500 target sentences, we can see obviously that it is better to use more target sentences. All the results are better when using 500 sentences. Then, even though one might expect that Italian would be a better transfer language for Latin because they are in the same language family, it seems that the optimal transfer language is Ancient Greek. And compared to Modern Greek and French, it seems that Modern Greek is better than French, even though French is more similar to Latin than Modern Greek. Moreover, we can see that the tree banks belonging to the same annotation projects tend to perform better. For example, when we both train in Perseus, and we have Perseus in Latin and Ancient Greek, we see better results than ProEL, but we also get good results using the ITTB tree bank, which has no parallel data at all. And also, there are 2 cases where even modern Greek outperforms Italian in parsing Latin, and the content of those tree banks is completely irrelevant. Then, apart from increasing the target language from 2,500 to 500, we also increased the transfer languages to 10,000. But we performed the experiments, as I said, only in ancient Greek and Italian. And in these experiments, we have slightly higher scores than before. So increasing the data size improves the results. And we can see that still ancient Greek outperforms the Italian tree banks. And lastly, concerning the monolingual experiments, we can see that in all cases, the multilingual models outperform the monolingual experiments. But we shouldn't forget that we have a low resource scenario. And to better illustrate the difference between the multilingual and monolingual models, we created this chart with data from multilingual experiments containing all the transfer language tree banks with 2,500 sentences and the target language tree banks with 500 sentences. And we can see the superiority of multilingual models as well as the superiority of the ProEL dataset, which seems to provide the optimal results overall compared to the Perseus ancient Greek tree bank. And lastly, we examined the similarity using the linguistic distances that Lin et al. Use, and we retrieved all the corresponding vectors from the Uriel typological database. It is available on GitHub. Anyone can have access to these vectors. And the values of the vectors range from 0 to 1. And the numbers close to 0 represent proximity, while the numbers closer to 1 represent that the languages are distant. And in terms of geographic distance, which is the first column, we can see that ancient Greek and Italian are closer to Latin compared to modern Greek and French, which makes sense since during the Roman Empire, both Latin and ancient Greek were spoken in the peninsula that now we call Italy. Concerning the genetic distance, which is the second column, we can see that Italian and French are considered more similar since they belong in the Italic branch of the Indo-European language family, and ancient Greek and modern Greek are from the Hellenic branch, so they are more distant. And their values are closer to 1. And then concerning the futural distance, which, as Sara mentioned before, is a combination of all the linguistic distances, we can see that ancient Greek is closer to Latin. In terms of phonetic distance, Italian and ancient Greek are closest to Latin. And finally, in terms of syntactic distance, ancient Greek is considered more similar to Latin, followed by Italian, then modern Greek, and then French. Based on these vectors, we use the Pearson correlation coefficient to see how these linguistic distances correlate to the parsing results. And we also performed a significance test to examine whether the correlation is statistically significant. From our results, we can see that we have a strong correlation between the parsing results and the syntactic and futural distances of the languages, suggesting that ancient Greek, based on the syntactic similarity vectors from the Uriel typological database at least, is significantly more closely related to Latin. Now, one might argue that using Latin as a low resource language does not provide enough data for the Italian models to outperform the ancient Greek models because we're using a low resource scenario. This is why we tried to demonstrate the results of using full tree banks. And in the first row, we can see the monolingual models trained on the full size of each Latin tree bank. And then we can see the multilingual models with Latin and the transfer languages. The Italian and ancient Greek tree banks have approximately 10,000 trained sentences. And we can see that even when increasing the Latin sentences, and we have no low resource scenario, the ancient Greek tree banks are better than Italian, especially in the Perseus tree bank has a really big difference. In the ProEL tree bank, we see a similar performance between the monolingual and multilingual models. And finally, we use all the Latin tree banks together, and we train a model with all the Latin tree banks together, and we see that the models outperform the multilingual models, suggesting why it is useful to apply multilingual models in low resource scenarios. And that we should always add target language data if available, of course. And now let's take a look at an example demonstrating how ancient Greek and Latin could be similar in syntax. This is the same sentence coming from the New Testament, and it is coming from the Proyel dataset available on GitHub. And then the same sentence is in Latin, and it's a word-to-word translation. We can see that both Latin and ancient Greek have a case system, which is expressed morphologically in the words. The case changes in the word, while Italian uses this preposition de, which causes a completely different syntax that could cause this to be not as syntactically similar to ancient Greek. And of course, this is just an example. There are more examples showing how word order is more similar to Latin and ancient Greek than Italian, apart from the case system, for example. And now let's reach a conclusion. How does training size affect the parsing result? So the more the data, the better. This was proven by all of our experiments. And it is more useful to increase the training data size of the target language than the transfer language. And this makes sense because the target language is the goal. And lastly, even though multilingual models perform best in the low resource experiments, this was not the case when they were trained with all the Latin tree banks available, which outperformed the multilingual models. Now, concerning the content of the tree banks, the impact of the annotation project seems to add to the performance, but it is not the main explanatory factor for the usefulness of ancient Greek, because we saw that the ITTB Latin tree bank, which is not from the same annotation project, has also really good performance with ancient Greek. Then the ancient Greek Perseus and Proyel tree banks outperform the Italian tree banks, also in the Latin ITTP tree bank, as I said. And finally, the tree banks for Italian VIT and the modern Greek and French tree banks have similar content. They are all news articles or political articles, but they have very different parsing results, indicating that language choice is more important than the genders of the tree bank, actually. And lastly, how does language similarity affect the results? And I think this is the most interesting question, because we found that Hellenic languages seem to be better for parsing Latin in a low resource scenario compared to Italic languages. And there are strong correlations between the parsing results and the futural and syntactic distance of the target and transfer languages, explaining the usefulness of ancient Greek. And the most syntactically similar language to Latin in our sample was ancient Greek. And this actually is quite intuitive because it is a parsing task, and the syntactic similarity plays an important role. And finally, we can say that language proximity is not always the best criterion to choose transfer languages. So we have to rethink when choosing transfer languages. And this was it. I don't know if there are any questions.
So I have one question. So I'm not very familiar with the Uppsala University parser, but I was wondering, so does it use attention of any sort?
No, it doesn't use attention. It uses the, as Sara had a slide. So it uses a swap and an arc hybrid system.
Okay, so I was thinking of the slide where you compared the Latin, Greek, and Italian trees, where you have this in Italian something that's encoded morphologically in Latin and Greek is a word on its own in Italian. So I was wondering if attention could help here to ignore this D.
Yeah,
I mean, a problem here could be that it puts as much weight on D as the other words when it tries to transfer. So maybe assigning a lower weight to this specific arc associated with this word could help.
Exactly. Actually, using a transformer model, for example, could overcome this issue, actually. But this was just an example also.
So maybe I can add there as well. We actually tried to add attention on top of the BiLSTM encoder at one point in time. We had a master student doing that, and he never really got any positive results from that. But I mean, that's on top of the BiLSTM model. Of course, transformers can be very useful. And there is a study by Ahmad and other that showed that for languages that have different word orders, transformers tends to be better than BiLSTMs. So I definitely think there is a case for using a transformer model instead. But I mean, in this case, we just used the UU parser. But yeah, it's an interesting question, is it? I think.
Yeah, so I mean, related to this, I was wondering whether you considered some sort of a measurement of morphological similarity between languages.
Unfortunately, the database that we used and all the database actually, the databases that we found had no vectors for morphological similarity.
Okay.
So,
so this is why we didn't use morphological similarity. There were
I wonder if this could be an issue, because if a lot of things are encoded morphologically, there won't be an arc, but rather it will be a tag in the UD.
But yeah, that should probably hurt more though if you're going from Latin to Italian and from Italian to Latin, I would assume, because then you wouldn't have seen these things.
Yeah, but I mean, what I'm thinking is that it could help selecting the languages. So you would take a language that has a similar number of words or arcs. I guess this is encoded in the syntactic similarity you have, though.
Yeah, I mean, it's taken from WALS. We didn't look in detail into exactly which WALS features they include. So it's possible that some of these things are also included in that, under that umbrella. I don't know for sure. But I mean, it's definitely something that would be worth investigating as well.
Thank you.
So maybe I should stop sharing.
Yeah. Then I'll just share it in here. Okay, so I'll continue with the third and final part then, where I talk a little bit more on different aspects of language choice. I'll present two studies, one on a more diverse set of languages, and one where we also take domain into account, and then I will finally wrap up. So in the first study, it's the work of another of my master students, Yifei Zhang, for her master thesis, where she explored the correlations with linguistic distances again from the URL database, and she was investigating the impact of using MBERT embedding versus using randomly initialized embeddings that we talked about before. She was also looking into zero shot versus joint training, and also again on the influence of training data size that Antonia already talked a little bit about. And in this work, we used the UU parser variant by Attardi et al., which also allows embeddings from MBERT. So we have 3 target languages here: Afrikaans, Greek, and Vietnamese. And for each of these, we have 10,000 training tokens. And we have a selection of 14 diverse, relatively diverse, at least, transfer languages. And there we set the size to 100,000 training tokens, because we want to control for size here, as we did in Antonia's experiment as well. But here we have a relatively large transfer language set and a much smaller target language set again. So again, focusing on the low resource scenario. So I just jump straight into results. These are a lot of numbers, so I'll guide you through them. So on the top here, we have the monolingual results. And this RD column is with randomly initialized embeddings, and MB is with a multilingual BERT. And we can see that this is Afrikaans and Greek and Vietnamese. So that for Afrikaans and Greek, we see an improvement around 5 LAS points when we add MBERT, the monolingual model. The Vietnamese, though, it actually gets worse by around 5 points. So it seems that Vietnamese is just not very well represented in the multilingual BERT. If we look at the results, we see that nearly all results with this randomly initialized model, they are really poor. I mean, the parser below 10 scores, it's a useless parser really. And this is not very surprising because there's really no cross-lingual signal at all here. This is mainly for comparison. We train parser on one language and then we just apply it out of the box without any shared representation for the word of anything. So you couldn't really expect this to perform well. The only exception is with the Dutch, because Dutch and Afrikaans are quite similar and probably have many shared word forms. So here we get a somewhat reasonable performance, even though it's not great. But all the other results are super poor. Even ancient Greek in Greek gives a very poor result. When we add MBERT, though, it looks better. So then we actually have a few good parsers for Afrikaans and Greek. So for Afrikaans, the related languages German and Dutch. German and Dutch performs best, especially Dutch again. For Greek, Czech and Bulgarian actually turns out to be the best option. So I mean, these are quite good results actually, getting an LAS of 50. For Vietnamese, though, I mean, there still are really no languages that give good parsers. So again, this seems to indicate that the Vietnamese just is not very well represented in the multilingual BERT. And again, these results confirm that closely related languages are often a very good choice. Then we turn to the joint experiments where we actually add some target language data, and now it looks much better. So compared to these monolingual results again, in essentially all cases, that's just the odd case where it doesn't get better. So regardless of which of these languages we use, we actually get improvements, essentially. That's an exception here with Chinese. But so that's very positive, of course, that just adding language from some data, it does help. But of course, we see that there's quite some difference between these results. So the strongest results are a lot better than the weakest results. And what's a little bit surprising is that Dutch is no longer the best option for Afrikaans. It has a good result still, but it's no longer the best option. So actually French and Japanese and Bulgarian in the different settings are now the best options. And it actually turns out that these languages are good across the board. So for all languages, Japanese, Bulgarian, and French performs quite well. And then there's some variation. Ancient Greek is also not among the top languages for Greek. It also seems that Ancient Greek is not well represented in MBERT. It's not in the training languages. And also both in the zero-shot experiments and the NIST experiments, Korean, Japanese, and Chinese performed really quite poorly and often lead to worse results. And otherwise, we mostly see improvements when we add MBERT compared with when we're not using it, but they're not as large anymore as they were in the zero-shot setting. And they tend to be a little bit smaller for Vietnamese than for the other two languages. We also half the size of the transfer language data. So instead of 100,000 tokens, we use 50,000 tokens, and the results are largely the same. They're of course a bit lower because using less data lowers the result, but they still beat the monolingual baseline in most cases, and the patterns are largely the same. So I already shown you so many numbers, so I don't want to push more numbers. I will push more numbers on you, but I skip that. So looking into the correlations, so these are the correlations with the same features again in the zero-shot setting and in the joint setting. The zero-shot results were so poor though, so they should really be taken with a pinch of salt because it's comparing super bad parsers. But still, there are some correlations here. I should also say that the bold numbers, that's correlations that are stronger than -0.4. So that's the ones that are relevant more or less. So for MBERT, for Greek, most of these features are actually have strong correlations, but otherwise there isn't so much. But in the cases where we have something inventory, which is a phonological distance, geographical distance, and pictorial distance, tend to be the best. For the joint models, which are actually good parsing models, so this is more interesting, I think, we see that there are many more correlations. But again, there are quite some difference between these three target languages. So it seems like language plays a role. And of course, these are in the European languages. So we had more Indo-European languages in our transfer language set as well. So both of these languages had closer relations than Vietnamese, which might have played a role as well. But the language choice does seem to play a role here. Also, we see some differences between these two models, especially here, which is not very surprising though, when we use MBERT and the randomly initialized embeddings. It's a little bit more stable in the joint setting. I don't have any correlations with the genetic descent of Vietnamese, by the way. It's because it's not related to any of them, so it wasn't possible really to calculate correlations. But overall, the featural distance is often quite strong, so that's a combination distance. And then we also, this is only for the joint MBERT model, we compared the two test sets, the dev set and the test set of these languages. And we also compared using all the data and half the data, as I mentioned. And then we can see that there are actually quite some variations between these two test sets. So this is most obvious here for Vietnamese, that these two lines are for the test results, which are strong for the syntactic distance, whereas the dev test isn't, and the opposite for the featural distance. So this is a little bit worrying, that aren't these results even stable across test sets? So I think, I mean, this really calls for more experiments. But even so, I mean, there are some tendencies that are quite strong. So the featural distance, even though it's not bold in all cases, is at least stronger than -0.3 in all cases. So that seems to be quite constant, that this is useful. And also this inventory distance, which is a phonological measure, which is again quite curious. Sometimes the syntactic distance is relevant, but far from always, which we would have thought a priori. But we see, again, just as in Antonia's experiment, that the size of the data doesn't really matter much. The results between the all setting and the half settings, the top and the bottom half for each, are largely the same. There are quite few differences. So to sum this study up, in the zero-shot setting, the results were very poor, but overall we saw large improvements when we're adding MBERT, which is not very surprising because that's how we introduced the cross-lingual signal. But even with MBERT, there was only very few transfer languages that gave acceptable results for ancient Greek and Afrikaans, and none of the transfer languages gave anywhere near an acceptable result for Vietnamese. In the joint parsing scenario, very nicely, nearly all transfer languages actually led to improvement over the monolingual baseline and in all our different settings. So that's very nice, that even if they're quite bad in a zero-shot setting, they can still be, these languages can still be useful when we have a little bit of target data. And also the transfer language choice shows some variation based on the embedding type when we had zero-shot compared to joint training. It varies with the different target language and slightly more worrying. It also seems to be a little bit sensible to test sets, which really calls for more experiments here. But what's nice is that it at least is relatively stable across the training set sizes. And we also saw that the featural distance was often relevant across all the different settings. So there was a little bit of signal constant across test sets, which was nice. So moving on to the next study, here we're focusing on improving dependency parsing for specific text types. And the focus was on Twitter and transcribed speech. So both of these are quite different from the typical things you would have in your tree banks, like news, Wikipedia, legal checks, and things like that, which are edited. I'm going to use the term domain here for this. Arguably, these are not really domains, but I mean, domain has been used for these kind of differences in much previous work. So I'm going to stick with that. But you know what I mean with domain at least. So the idea is that we can create good parsers for this text types by combining parsers, and specifically to combine in-language data that is out of domain with in-domain data from other languages. Because we only have tree banks for these text types for quite a low number of languages. So we can't expect to have it in all possible languages. So just as a motivation, this is an example of a spoken Norwegian sentence from the Norwegian tree bank. And there are a lot of things going on now that you wouldn't have seen in edited text. So you have this then, so you have things like fillers, there's a referendum, there's a word that is repeated, and here's a word that's replaced by another word. So you have these very specific archetypes that you wouldn't even have seen in many tree banks for many languages. So how could you even, I mean, you couldn't really even parse this unless you have some data where you have actually seen these relations at all. So that's the kind of motivation for why we want to combine this in-domain tree banks across languages. So the languages we use here, it's based on availability of tree banks for this text. For speech, we have tree banks with training data for French, Norwegian, and Slovenian. And we also have test data for Niger and Commissarian. And for Twitter, there's tree banks for English and Italian. And there's also really challenging tree banks with Hindi-English code switching tweets. These, again, labeled attachments for evaluation. And I haven't really talked so much. I mentioned these tree bank embeddings. And in the experiment so far, we have always included the target tree bank or the target language in the training data. So then we can just apply the tree bank embedding for that language, except in the zero-shot experiments, but then we just train on a single language. So then we could just, again, apply those. But in this setting, we don't have the target tree bank among the training data. We have tree banks that match the language and tree banks that match the domain, but not which matches the combination. So we need to have some kind of method for setting these tree banks embeddings at the test time. So one method is to use what we call a proxy tree bank. So just pick one of the training tree banks and use that tree bank embedding. And we need to make that choice somehow. And one way to do this is to apply all the possible tree bank embeddings on the dev data, and then based on the scores there, choose the best proxy tree bank that we can use on test data. Of course, we need to have dev data here, which we don't always have. So we also compare this to parameter-free methods, where we try to find ways to handle this without using development data. So in the first case, we just simply interpolate embeddings of all the possible proxy tree banks. So we just average them. And this is actually, it actually works quite well. And it's a good fit for this particular situation because all the training tree banks are relevant to the target text in some way. They either match the language or they match the domain. So just averaging this kind of makes sense in this scenario. It wouldn't always make sense. There's some work on weighted interpolation by Wagner et al., which is quite interesting, but that's in a monolingual setting. And we also train ensembling methods. So then we parse the test sentences using all proxy tree banks. And then on top of this, we apply the Julie-Edmonds algorithm, where we weight each arc by the number of trees that contains this arc. So this is a much more computationally expensive method because we need to parse the test data multiple times and then also apply a CLE pass. So these are the main results. So this is with the proxy tree bank. So on the top line, we just use out-of-domain data for the same language. On the bottom line, we add this in-domain data from another language. For each language, we use the other two. So for French, we use Norwegian, Slovenian, and so on. And this is, the middle line is a control experiment where we add an equivalent amount of data from the same languages, but which is also out of domain. And you can see that for 5 out of these 6 languages, we see some improvements, which are strongest for Slovenian and Italian, and also on average. Norwegian is a little bit of an outlier. That's partially, we think, also because instability. If we repeat these experiments, things got a little bit more as expected. And here we compare these 3 methods, the proxy tree bank, interpolation, and ensembling. And we see that ensembling isn't always successful. In all cases, either interpolation or a proxy tree bank gives the best results. The interpolation is never too far off, but sometimes the interpolation is much better than the other tree banks, especially for Slovenian and English. So, and interpolation is the most efficient method, and so that's very positive as well. Here I also show which are the tree banks that were used as a proxy. So in all cases, at least on these 5 top lines, it was the tree bank matching the language, what more useful than a tree bank that matched the domain, but from another language. In the last case for Hindi English, we don't have any other Hindi English code switching tree banks, so we have to use separate Hindi and English tree banks for training. And in that case, actually the English tweet tree bank was the best, which is not very surprising because it's actually partially matches the language and it matches the domain. Here's also the result for these 2 low resource languages. So we can't really use the proxy tree bank unless we just make a guess because we don't have any development data. So we're just comparing interpolation and ensembling. So here is when we we don't have any data from the same languages. We have to use out-of-domain data from related languages or neighboring languages. But when we add the other in-domain data, we see that we get improvement, especially again with the interpolation method, which is nice. So to sum this study up, combining tree lengths across languages and domains are definitely feasible. We see small but quite consistent gains from adding in-domain tree lengths from other languages. And the proposed parameter-free methods, especially the interpolation methods for handling tree-back embeddings, works really well in this scenario, which is also nice. So to sum up the full talk, so we have presented 3 studies that focus on different aspects of language choice. In our first study, we investigated whether Hellenic or Italian language is the best as transfer languages when targeting Latin. And we found, as Antonia told you, that Hellenic languages, especially ancient Greek, are preferable. In the second study, we investigated which transfer languages to choose from among a diverse set of languages under different conditions. And we found that only a few transfer languages gave an acceptable performance at all in a zero-shot setting with MBERT. But most languages improved results in a joint training setting. And in the final study that I just told you, we found that it's useful to match also domains across languages, especially, and in this case, where you're targeting very specific domains that are different from other types of text. So if we talk about transfer language choice, so in the Linatol study, they suggested that geographical and phonological distances were the most important, and also word overlap, which you didn't explore in our studies. This was in the zero-shot setting though, and as we see, the results are often very poor in the zero-shot setting, so should probably take this with a little grain of salt. In our Latin study, we suggested syntactic and featural distance are the most important measures. In our second study, all the different URL distances were shown to be useful in some setting, but overall, the featural distance seems to be the most stable one that in more or less all settings gave quite a good indicator of which transfer language to use. And our final study also showed that matching domains can be very important. And it is probably useful to combine different measures. I mean, this is the main conclusion of Lin et al. And also the fact that featural distance is so often useful, which combines these other different linguistic measures, also indicates this. It's probably hard to find a single indicator that will work across the board. We also think that it might be worth handling situations where close target languages are available differently from cases where they are, because it seems that if you have a close relate, that's often the best case, even though it wasn't always the case that Dutch was the best option for Afrikaans. So that also needs to be further investigated, I think. But definitely in a case where you don't have any closely related languages, you need some kind of other measures to decide which language you're going to choose. And I think there's much more that can be explored in this space than we presented today. And there are also, I mean, we could go more in depth in the aspects that we already studied, but there are also many more aspects to explore. So except for the last study, we didn't really look into multi-source transfer. We just looked at single source transfer, where we mainly looked at single source transfer, at least, where we have a single transfer language. But what about the case where we want to transfer from multiple languages? How should we choose that? Is it better to choose all by the same criteria? Maybe by just choosing the, say if we want 3 languages, the 3 most closely related languages? Or is it better to, in that case, to choose a more diverse set of languages, maybe one genetically close, maybe one geographically close, and maybe one with a low syntactic distance or with a high word overlap or something like that. And that's still to be explored. Also, language choice is important when we target the specific languages, a specific language we mainly talked about today, but how should we treat it for models targeting many languages? Then there are many trade-offs. I mean, you want to have a model that works well across a large range of language, but there are also going to be some trade-offs. So that situation is even harder to evaluate, but it's still really worth investigating, I think. You could look at other parsing models and architectures. And it's also interesting, I think, the trade-off between target language annotation and cross-lingual models. We saw that there was some variation between the zero-shot and the joint models, for instance. And I mean, how does this vary when you have a little data and when you have more data? And eventually, when you have enough data, it's probably better just to use the monolingual model. But where is that point? It's also an interesting point. Another line of work would be to find better ways of quantifying language distances. We had the question about morphological features, for instance, which is probably a useful thing. One issue with these linguistic distances is that they're based on these linguistic databases, but for many languages, there are missing values, which of course would affect these distance computations. And it could be the case that this happens more often with low resource languages, but at the same time, many low resource languages are quite well documented by linguists. So it's not always the case that we have bad estimates there, but there's definitely an issue with these measures. So, and there could also be, of course, better measures that we didn't explore, or other aspects that are also important. And I think another kind of interesting question is that if we have a limited budget for some target language, if we have an expert, but we can only pay him for a few hours of work or a day of work or something, how should we spend that in the best way? Is it better to get the typological description of a language? Is it better to create a dependency annotation for a few sentences? And if so, how should we select those few sentences? Maybe some kind of active learning or something? Or maybe it would be really useful to have the post text for a set of common words, so you at least, which would probably be faster. So, and I think this is quite a realistic scenario. So I think that would also be a very interesting line of work that connects to what we talked about today, and how to combine potentially some kind of partial information into the parsing model. So thank you very much for coming to this talk.
Yeah, thank you so much to both of you for putting these together and spending your time both on the presentation itself and then taking the time to share it with us. It's quite a bit to think about. That's also going to be pretty useful. I think that line of work is going to be it raises really interesting questions about how, like, what these trade-offs are, and like how that time and how those resources should be.
Oh, now you muted yourself.
Oh, sorry. Yeah, no, yeah, I didn't realize that I had hit mute, but where did I cut off?
Just the last couple of sentences.
Oh, okay, got it. I was just saying, like, it raises some really interesting questions about how those resources can be used, and especially around looking at like low resource languages where there's where you may not have a high number of options. So this is particularly interesting. But I'll turn it over to, I guess, Adam, Priya, and Atul. Sorry if I'm mispronouncing your name. If you have any questions.
Hi, Sara. Thank you very much for the talk. I have a question. So when we talk about the transfer language choices, so if the choices are similar languages or closely related languages, then there are chances of a kinds of word overlap or syntactic overlap, and there are lots of ambiguous words which behave quite differently even in the similar languages. So what effect does this kind of scenario create? Like, I mean, how does it affect when you train the model and in the accuracy of the models?
Yeah, sorry. So can I just repeat how I understood your question, just to see if I got it right? So you're saying that there are a lot of ambiguous words. I mean, both within a language, but maybe even more across languages. Is that right?
Yeah.
So I mean, of course, that affects the parsers to some extent. When we're adding MBERT, of course, then you get a contextualized representation. So those representations could take that into account to some extent. I guess depends a little bit. Good. In these models where we don't have any contextualized representation, of course, we have the BILSTM in our parsers. So I mean, then you also get contextualized representations to some extent. But when you're sharing language information across languages, I mean, it depends a bit. I mean, this randomly initialized embeddings that we learn as part of the parser training, of course, they're going to be affected. So if there is a word in one language, it just happens to coincide with a word form in another language, meaning it's completely different things. I mean, that's going to disturb the parser. And but I guess overall, if two languages share a lot of the vocabulary, I mean, that's I mean, even if there are a few false friends or word forms that happen to coincide, you probably get more of a gain in the bigger picture, but of course it can disturb a bit. And of course, when we use cross-lingual embeddings or MBERT and representations like that, that's hopefully going to help us a little bit with representing this in a better way. But as we saw, I mean, we get some gains from MBERT, but still, I mean, it's often not a massive gain.
Okay, thank you.
Hi, Sara. Thank you for this nice presentation and the detailed result discussion. So I was wondering if you could go back on your slide, joint results and transfer zero sort. So
sorry,
can you go back to your joint learning results on joint learning results?
So this one?
With MBERT, yes. Correlation.
Okay, this one, yeah.
Yes. No, can you? Okay. In some slides you have mentioned in some places MBERT was not performing well, including Chinese. But I'm not. I'm definitely Chinese has a different features for Vietnamese and African languages. But in some other languages, MBERT was not giving good result. So I'm wondering if you have any idea why it is not working properly, not giving better result.
So you mean
yes, this one?
So, I mean, yeah. So I know that also is the work of some other people. It has been shown that Chinese is not really well represented in the multilingual BERT. So I'm not an expert, but I think the way they tokenize Chinese into characters is a little bit different from the way they tokenize. I mean, it's harder to tokenize Chinese to start with, but they might not have done this in a very principled way. So there seems to be some issues. If you want good results on Chinese, you shouldn't really use MBERT. There are models more specifically targeted at Chinese, which do perform.
Yeah, Chinese and Urdu has a different script. I understand Urdu and Chinese has a different script.
Many of these languages have different scripts. So I mean, the top ones here are the ones with the Latin script, and then we have Arabic, Urdu, and then we have a couple with the Cyrillic script, and then some other scripts, the Greek. So I mean, yeah, it's only these top ones here that has the Latin script as two of these target languages. And I think I'm pretty sure ancient Greek isn't in the multilingual BERTs. I mean, if the language isn't in the training data, it probably has the worst representation, which could be a reason why ancient Greek was never a good choice for modern Greek.
Okay.
But yeah, it's hard to say. I mean, exactly what's what here. I mean,
no, I'm just because I'm.
But yeah, I think
I'm
it's
very interesting to know reason. What is the reason behind? Because it is working. It gives better result in other languages except few languages.
Yeah, and for some languages like Urdu, for instance, it does help for Afrikaans and Greek, but not for Vietnamese. So I think Vietnamese is a bit of an outlier here because it does seem to be quite poorly represented in MBERT. So it's probably more relevant to look at these two languages if you're interested in languages where MBERT has a reasonably good representation, at least. Of course, it might be interesting to have good performance also across other languages. Then the Vietnamese case is probably more interesting.
Okay, great, thank you. And maybe I'm wrong. You have mentioned in your talk Hindi doesn't have a code mixed data or code switched data, tutor data, and based on dependency.
Yeah, there is a tree bank in UD that has Hindi English code switched Twitter data, but there's no other Hindi English code switched data.
Yes.
So for when we wanted to compare it to using matching tree banks that were out of domain, we had to use separate Hindi and English tree banks. So that's of course different from the code switch situation because you'd never see Hindi and English mixed up in the training data. You just see it separately compared to the target data where you have Hindi and English in the same sentences. Yeah, so it's really a challenge to parse this code switch data.
Yeah. Thank you.
Yeah, thanks.
Thanks for a very nice talk. It was very interesting. So I have one question about the last experiment you presented with the in and out of domain data and in relation to the case study on Latin. So in the case study of Latin, you found that using in-domain data, so for example, Bible texts, didn't help, right? So it wasn't a significant factor when selecting languages.
Well, I mean, we found, I mean, there were kind of two factors there. I mean, one was that the data type was the same. Another one was that actually the annotation project was also the same. So you would have had more similar guidelines. So it's a little bit hard to compare because here all the annotation projects are different. But I mean, we saw that the results were actually better when you matched the annotation projects, which also partially matched the data. But we still got good results even when we didn't do that. So they're a little bit different in the setups. So here we teased it apart a little bit more, I'd say, than we did there.
So, well, I was sort of wondering if this could help identify which domains could be nice to transfer from. Since, I mean, biblical text didn't seem to have a large impact. I mean, you didn't try any other things
No.
out of the in-domain here.
No.
So
in this study, we just looked at this whatever.
Right.
Different.
Well,
but
yeah.
I think it would be interesting to do this for more standard than speech and Twitter also, to look at Bible and legal text and things like that you also have in UD. But yeah, we didn't really do that in depth.
Yeah,
there's so many directions. There's so many things you'd like to do.
Yes, and especially like when you're sitting on the sideline, too many ideas pop up.
Yeah.
I also had a question about the MBERT experiments.
Yeah.
So I was wondering if you tried to correlate the improvement you got with the amount of training data used in training MBERT.
We didn't actually do that, but it's a great idea.
Well, I think it's maybe somewhat disproved by that essentially all languages got a negative, or most languages got a negative difference in the Vietnamese case. So there, like the training data used in MBERT don't really seem to matter. But maybe for Afrikaans and Greek, the amount of training data in BERT, when that corresponds to
yeah. I think that would be really interesting to try that out. That's a great idea.
Yeah, thank you for answering all the questions and giving this talk.
Yeah, thanks.
I don't have any further questions. Priya, Adam, Atul, do you?
No, thank you, Joe.
Yeah, I just want to make sure that we give you guys your time back as we get to the hour-and-a-half mark. So, because it's already what is it, like 8:30, something like that in Sweden. So, thank you so much for taking the time, especially Friday night. So it's very much appreciated.
Yeah, thanks.
Thank you so much also for the nomination. It was a great experience.
Well, you're off on a strong start before you venture into your academic career. So, or I guess that's already started, but at the doctoral level. So, yeah, thanks so much for taking that time to come here and share your research. So,
yeah, thank you for listening as well.
Well, hopefully we'll see you all around. We do SIGTYP talks every week, so it would be great to see you all again.
Yeah.
See you. Bye-bye.
Thank you. Bye-bye.
Bye.
Bye. Thanks.
Thank you.